This conference will now be recorded.
So guys, today we will be looking on to how we can construct the minimum spanning tree. It's gonna be algorithmic exploration for Prim's algorithm to create a minimum spanning tree out of your graph, right? So we'll take the same example, the yesterday's example, in which we already know that what minimum spanning tree is all about, right? So we know that it's gonna be 0 to 1, then 1 to 3, then 3 to 4, and 3 to 2, right? So these are the edges which are going to form a minimum spanning tree. So other than this, so this edge 0 to 2, 1 to 2, and 1 to 4, they were creating cycles due to which we cannot add them, right? So Prim's algorithm, we need not to work on cycles somehow, but at the same time, right, with the Prim's algorithm, we are going to use a different approach and we'll be evaluating your MST, but there you need not to come up and look for the cycles, right? So it's a different approach to solve the same problem, basically. So let us start with the Prim's algorithm discussion, and we'll have an algorithmic discussion. We'll see what it is gonna do, and thereafter, maybe tomorrow we can code it. So I'm gonna have this a new file, right? And we'll be seeing the discussion here. So lastly, we'll see the visualization. So I got this uh, graph, right? And we're gonna work on the same graph. So just give me a moment. Just very quickly. So this is the graph on which we are supposed to work, guys. So how you'll be working on Prim's algorithm, right? So we have a small okay, so just give me a moment. So this is sort of not working somehow, some exceptions. All right, so I hope this font and all is visible to everyone, guys. If you want, I can increase the size. Please update me in case we are good to go with the font size. So guys, the visibility is fine to everyone, right? All right. So in the Prim's algorithmic discussion, so we are going to evaluate and understand how we can approach towards this guy called MST. So the very first thing in the Prim's algorithm is associate an infinity weight with all the vertices. So what we are considering is we are considering an infinity weight with all the edges of your graph, right? So how you gonna understand this is that this guy is going to be infinity weight, this guy is going to be an infinity weight, right? This is the vertex with the weight, right? So we are associating one weight with the vertex as infinity. So there is one weight with the edge, right? And I'm not gonna associate this infinity weight to zero. All right. So for my zero, I'm gonna say the weight is zero. To begin with, I'll start from zero. My algorithm will start from zero. So how will you be able to associate infinity weight? So if you want to associate an infinity weight to your vertices in the graph, so programmatically you will be looking forward for the max number. So max number in Python, so that you will just say your import sys, and thereafter you can say sys dot max integer. So you can get your maximum number. So here what we are going to do is we are having a dictionary of vertices with sys dot max int as weight associated with it. So every vertex is going to have a weight associated with it here. So is this first step clear to everyone, guys? Number two, we are going to choose 0 as our vertex from where we will start our algorithm. So what I'm saying is we need to define this prims as algorithm right in our so guys, I can remove this infinity, right? I'm just gonna clear off this infinity part, right? So this was for the understanding of us. All right. So let me save the same document at the same time. So this is going to be defined in your class graph, right? So there will be self and the vertex as input, right? So this vertex is going to be the zero vertex from where you are going to start, right? So that is what we are saying. So the Prim's algorithm has to start from some source. So we choose zero as our source vertex to begin with. So guys, if you want, you can open up this graph from the visual algo, right? So I'll share this link over the chat. So this is the graph which you are actually following from visual algorithm. Okay. Now, what I'm going to do is I'm going to maintain some list of, you can say, so maintain few lists as below. Let's see, guys, what are these lists and how I'm going to maintain it, right? I'm gonna write all the vertices. So what is the vertex? Then I'm going to write the parent to the vertex. Then what is the weight at vertex? So these are the three lists which I have to create first of all. So there are these vertices 0, 1, 2, 3, and 4. So who are the parents to these vertices? So I'm gonna say none. There is no parent to the vertices. So these are the three initial lists which we are going to maintain. And what is the weight at vertex, right? So the weight at vertex is this sys dot max integer. So when I'm saying this sys dot max integer, right? So what exactly the value of this guy gonna be? So let's very quickly see. So there has to be this new Python file, session number 37. So I'll say import sys, let us say define main. So print me sys dot, right? So let's say some max size. Let me check. So this is your maximum number, right? So the API is this max size, right? So this is what you got as in a maximum number, right? Infinity. So for a better understanding, right? So as this is not max int, so I think it's max size here, right? So for a better understanding, I'm gonna say that this is infinity for us, right? So this max size is kind of infinity for me. So you can consider this as infinity, right? So very quickly, I'll just put this as max size. Can I get a smiley from all of you? Is this clear, guys? So we are maintaining some things there, right? Vertex, then who is the parent to the vertex and what is the weight at the vertex? So what I can do is here we can create a dictionary of vertices, and key is vertex and value is list which contains parent comma weight at vertex. Can I get a smiley here? Are we good to go till here, guys? Anyone having any challenge till here? So three lists which you have to maintain. Then two more lists which you need to maintain. So there is this first list called visited vertices, and the second one is unvisited vertices. Visited vertices, and there is going to be an unvisited vertices. So these are the two lists which you have to maintain separately. So by default, there is no vertex which you are going to visit. So you will say 0, 1, 2, 3, and 4. All of your vertices are unvisited as of now. For my algorithm to work, I need to associate an infinity weight with all the vertices, right? And other than this, so what we got is we got this 0 as the source vertex from where we'll start, but we need to maintain the list as below. Now let's see how we're going to deal with this part, right? So let us start from 0. So when I will start from vertex 0 as the source, so I'm gonna say start from vertex 0 as source, right? So I need to maintain this table. I mean to say this list somehow. So who is the parent to 0? So you see the 0, there is no parent, right? So we are not approaching 0 from anywhere. 0 has no parent. So what I'm gonna do is I'm gonna say let the parent be -1. Since we have no parent for this guy 0, you're gonna make the parent for this 0 as -1. You started from here itself, right? You started from here. And I'm gonna now replace this max size with 0. So I'll assume that this vertex from where you're going to start your Prim's algorithm is 0, right? And the weight is 0 here, and the parent is -1. When I'm saying parent, you'll very quickly come to know what exactly the parent is. So till now in our assumption, so these visited vertices and the unvisited vertices, they are in the same manner, right? So this is like from where you want to start. Now in the next part, what we are going to do is, so explore or visit adjacent vertices to 0 one by one, right? So now I'm going to visit the adjacent vertices to 0 one by one and capture the weight on the edge, capture the weight on the edge and update that weight with vertex, with visited vertex. So let us see what I'm trying to put here. So from 0, you're starting your algorithm from 0. So from here you're going to come, right? At the same time, this 0 for us as of now is having the weight as 0 at the vertex, and the neighbors to the 0 are 2 and 1, right? So when I'll go from 0 to 1, so this is already having an infinity weight and this vertex is already having an infinity weight. So what we are going to do is, when I visit from 0 to 1, when I visit from 0 to 1, the weight is 9. So I'll update the weight at 1 as 9. So the weight at edge will be updated as 9, but only in case this weight over here is less than infinity, which is, right? So 9 as the weight on the edge is less than at the weight which is there on the vertex. So we update the weight at 1 by 9 and we mark our parent to be 0. Same way, when you visit from 0 to 2, right? When you visit from 0 to 2, so you are at 0 only. As of now, you are visiting 0. So visiting a vertex means exploring the adjacent vertices. I repeat here again, visiting a vertex means explore the nearest neighbors, adjacent neighbors, I mean to say, not the nearest, adjacent neighbors, and update their weight. So I'll very quickly now go to 0 to 2, and this weight will now become 75 because your infinity is greater than 75 and you have this 75 lesser than infinity. So not very good at drawing somehow, but even though managing. Okay, so what is the next part here? So this is where we have to, this is the starting, this is you have visited 0. So when I have visited 0, in the visited vertices you got this as 0. From unvisited you're gonna remove this 0. So what you're doing is you're trying to maintain a queue, right? So in the queue, 0 is coming as the first one to visit, so you just pop it off, you remove that guy from the list since you have visited. So unvisited now are 1, 2, 3 and 4. Visited is 0. Now when you visited 0, so 0 had these two neighbors 1 and 2, these two adjacents, so the parent became 0. It's not none now, the parent became 0, and this max size was very higher as compared to their weights. So from 0 to 1, the weight was 9, and 0 to 2, the weight was 75. So here the weight became 75. So guys, can I get a smiley here? Are we good to go? The step number 4 is clear to everyone. Acknowledgements awaited from all. Wonderful. Now what we need to do at step number 5, let's see. In my 5th step, now from the unvisited vertices, so from unvisited vertices, pick up the vertex with least weight and explore its neighbors or explore its adjacent vertices. To adjacent vertices one by one and capture the weight on the edge and update that weight with the visited vertex in case weight is lesser than weight at vertex. So let us see what I'm trying to put up here now. So from the unvisited vertices, that's like 1, 2, 3, and 4. So these are the unvisited vertices. Who is having the least weight? I think 1 is having the least weight at the vertex. So from unvisited vertices, pick up the vertex with least weight. So this least weight vertex for me is 1 with the value as 9. Right? Then explore its adjacent vertices. So who are the adjacent vertices to 1? Let us see here. So the adjacent vertices to 1 are 2, 3, and 4. So we got this, sorry, 0 as well, right? So 1, 0, 1, 2, 1, 3, and 1, 4. So I'm gonna write here. So you have this 0, 2, 3, and 4. So you need to visit one by one and capture the weight on the edge and update the weight with the vertex in case weight is lesser than the weight at the vertex. But there is a small quick update here. So when you have to explore its adjacent vertices, so you're gonna explore adjacent unvisited vertices. Now out of 0, 2, 3, 4, so these are the adjacent vertices. So these are your adjacent vertices. And your unvisited out of them are what? So unvisited vertices are your 2, 3, and 4 from this list. So can I get a smile here, guys? So you're not going to come up and visit this 0 again, which is the adjacent to 1. Why? Because you already visited 0 and explore its neighbors. Remember, visiting 0 means exploring the adjacent vertices or the neighbors. So it doesn't mean that the 1 is visited and 2 is visited, right? So you are only visiting 0 and exploring the adjacent vertices. So can I get a smile here? Now what I'm gonna do is, for these unvisited 2, 3, and 4, which are adjacent unvisited vertices to your guy 1. So you're gonna go to them one by one, right? So from my vertex 1, I'm going to go to this vertex 2 and check what is the weight. The weight is 75 here, if you see. So from 1 to 2, from 1 to 2, when you go here, the weight on the edge is 95, but the weight on the vertex is 75. So since the weight is greater, you will not update the weight at 2. So once again, right? So this weight 75 over here is lesser than this weight called 95. So do not update. Let us see the next part. So when you go from your 1 to 3, right, what happens? So when I go from 1 to 3, so from 1 I need to go to 3. So 3 has the weight at vertex as max size, which is greater than what? So which is greater than this 19. When you're going from 1 to 3, the size is 19, right? It is greater than 19. So this is greater than 19. So update, right? And when I'm gonna do an update, so with the update part here, this becomes 19 and the parent becomes 1. Why will the parent become 1? So initially the parent was none, right? So you're gonna update both parent and the weight at vertex. So can I get a smiley as an acknowledgement from all of you? So please ask me your query anytime where you feel like that, okay, this is not getting clear to us. Okay, now we need to go from 1 to 4. So when you go from 1 to 4, you get the weight at edge is 42, right? So when I'm going from 1 to 4, so this max size over here is greater than this 42. So update. So we are going to come up here and say the new weight is 42 and the parent becomes 1 again, right? Because you are visiting from 1. So the parent is that fellow from where you are visiting. So this is your iteration when from your list you actually visited this fellow 1. So you visited 1 and this is your unvisited vertices now, right? So you update your visited vertices and unvisited vertices at the same time. I hope this is also clear to everyone. Now the same steps are supposed to be repeated again and again, right? So let's see the step number 6. Now from unvisited vertices, pick the vertex with the least weight. So these are the unvisited vertices, guys. 2, 3, and 4. Let us see 2, 3, and 4. What I think is out of this 2, 3, and 4, right? So out of this 2, 3, and 4, so just give me a moment. I'm just gonna have these colors like this. So we need to pick this fellow called 3 because 3 has the minimum weight at the vertex. That's like 19, right? So we're gonna pick 3 because 3 has the minimum weight as 19. So we need to explore its adjacent unvisited vertices. So for 3, who are the vertices which are adjacent? So for 3, I got 1, 2, and 4. So we got 1, 2, and 4. So these are the adjacent vertices, but who are unvisited, you need to look from here. So these are visited, right? 0 and 1 are visited. So I think we only need to visit 2 and 4. Since 1 is already visited, so you need to only visit 2 and 4. One by one. And all right, I think we need to come here and manipulate this fellow. So we got this guy as 1. Just give me a moment, guys. This is 0, 2, 3, 4, and 2, 3, 4. Right. So for 3, we got these 1, 2, and 4 as your adjacent vertices, 1, 2, and 4. So out of 1, 2, and 4, so 1 is already there in visited. So you are not going to, sorry, 2, yes. So 1 is already there. So you're not going to pick 1. So you have to only visit 2 and 4, one by one. So let us go from this vertex 3 to vertex 2. So when you go from 3 vertex to 2, so 3 to 2, when you go from 3 to 2, right? So the weight is 51 on the edge. So let us see the weight at 2. So when you go from your vertex 3 to vertex 2, the weight on the edge was 51, right? So for 75, which is greater than, so this guy 75 is greater than 51. If you see this weight on the edge, 51, right? From 3 to 2, 75 is greater than 51. So we are going to do an update. So update. So this 75 will be now 51. And at the same time, the parent to this fellow, so this 51 is the weight which has been updated, and the parent for this guy 2 becomes 3. Guys, can I get a smiley from all of you? Are we good to go till here? What happens? What happened when you visited from 3 to 2? So the weight on the edge was lesser than the weight at vertex. So we updated the parent and we updated the weight at vertex. Acknowledgement waited from all of you guys. I hope this is clear. So you are updating this weight and parent both. Wonderful. Now in the next approach, right? So you have to visit this fellow called 4 from 3. So when you visited 3 to 4, so what you see is the edge is containing the weight 31, right? So coming here, you're going from 3 to 4. So 42 is the weight at the vertex, which is greater than 31. So update weight and parent. So the weight will be updated as 31 and the parent becomes 3. Can I get an acknowledgement now? I think this is clear, right? So this will make the next visited fellow as 3 and will remove the 3 from here. So this added here, and this is your new list which has been created for the unvisited part. So you see the number of steps which we are trying to perform, guys, right? So these are the number of steps which you have to perform when you're writing this algorithmic approach. Now from 2 and 4, which are unvisited vertices, so 2 and 4, I think 4 has the lesser weight, right? 31. So you're gonna pick this guy called 4, whose weight is going to be 31, and explore its adjacent unvisited vertices. Let's see 4. So 4 has these two vertices, 1 and 3. 1 and 3, right? So for 4, you got 1 and 3 as the vertices which are adjacent. So the adjacent vertices are 1 and 3. So are they visited? Just give me a moment here. This is our step number 7. So we got this 4 with 1 and 3. So you're gonna check, are they vested? So guys, they are vested, right? So unvested vertex is what? None. So you're gonna skip this step. So this step has to be there, but you are going to say that okay, we vested 4. Right? So we vested 4 and this is gone. So now you are left with only last option. That's like you got this guy called 2 as your unvested vertex, right? This is now going to be an empty, and here you're gonna add this guy called 2. So we got 2 as the vertex and 2 as the weight of 51. So you're gonna explore its adjacent neighbors. So 2 as these adjacent neighbors as 0, 1 and 3. So 0, 1 and 3 are the adjacent neighbors to this fellow. I think they are already visited. They are already visited, right? So you cannot visit any other vertex. Guys, can I get a smiley here? Are we good to go? Anyone having any challenge? So let's come to the visual algorithm visualization here. Visual algo visualization. So we'll run this Prim's algorithm from the 0. Let's say go. So what is this resultant algorithm doing for us, right? Let's see that as well. So this is the resultant image. So I'm gonna come here, and this was the last step, right? So our algorithm will stop here as we have no more unvisited vertex. So let me come here and see picture from file. So guys, this is your final result, right, which you should be obtaining. So let us see. So we got this 1 0 or 0 1 is 9. So this is my final table, right? So let us see this final table. So you got this 0 to -1 and 0 from where you started, right? So this you need to eliminate. So what you see is 1 to 0 has 9. So this is there. 0 to 1 or 1 to 0, right? Then you got this 2 to 3 or 3 to 2 with 51. So this is there. Then you got this 3 to 1 or 1 to 3. 3 to 1 or 1 to 3 with 19. It's there. And lastly, you got 3 to 4 or 4 to 3 with 31. So these are the 4 edges with which you need to create the MST, minimum spanning tree. So with above details from vertex, parent and weight at vertex, create minimum spanning tree. Guys, acknowledgement awaited from all of you. I hope this part is clear to everyone. So this Prim's algorithm is clear to everyone. So very quickly, right? Coming here with our session number 36 as done yesterday. So you had this class called edge graph. You added the edge, removed the graph, printed the edge, kind of sorted the edges. So I'm just gonna have this entire program. So this is the same program, right? And in the graph, you need to do a bit of changes here. So I'll tell you what changes you need to do. You don't need remove edge. You're not gonna sort the edges somehow. You're not gonna sort the edges. There is no crucial to be executed here. So you have this guy called run prims, and you need to have this vertex from where you're gonna start. The source vertex to be precise. Right? So this you need to implement. I think algorithm is clear. I'm just gonna give you some more inputs today. How you gonna work on this? So edge has vertex 1, vertex 2, and the weight, right? So you are maintaining, you are not supposed to maintain edges. So if you want to maintain, you can maintain the edges in the graph, right? But what I'm gonna do is I'm gonna maintain few things here in my graph. So what are they? So I need to have list of vertices, the parents to the vertices, and the weights at the vertices, right? So when you are going to create these vertices as a list, I mean as a dictionary. So while adding the edge, so you add this dictionary, in the dictionary you add this vertex and you create this adjacency list, right? So you're maintaining this adjacent vertices over here. So what I'm gonna do is, so these are like vertices, and I'm gonna say self dot let's say vertices. So this is going to be your adjacency list to be precise, right? So this is also going to be a dictionary for us. So this adjacency list will be replaced with the vertices. So guys, I hope this makes sense to everyone. So I'm just gonna replace this terminology, right? So we are just going to the vertex from where you wanna begin, right? That's like your zero. So here I'm gonna come up and add this edge, right? When you add the edge, you are going to manage these edges in your graph. Okay, you can manage that. In the adjacency list, you're going to add the adjacent vertices in the list, right? Of course. So you're adding these adjacent vertices in the list. So in the vertices, I'll say self dot vertices of edge dot vertex 1 is also a list, and this guy is also a list in the vertex 2. So you are maintaining one more list, right? So the previous list was your adjacent vertices, and this new dictionary, which is vertices, right? is going to have all the vertices and you have a list. So typically what I'm doing is, this guy is a dictionary, vertices is a dictionary, where in the list I have parent as none and weight at vertex as sys dot max size. So what I'm gonna do is, in this list the parent is none, so 0 index is the parent and the first index is your sys dot max size infinity. Same goes for this fellow. So it means initially when you will print out your vertices, right? So this is like printing the graph, printing the edges. So I'll just come here and say define print vertices. So you want to print down the vertices. So you get a number of vertices in your graph. It's going to be length of vertices. So keys in the vertices, right? So we have this key coming out, and from the key you will get one list for key in keys. So I'm going to come here and say print me. So guys, I'm just going to have these three things printed for me. Let us see what are they. Dot format. The first one is the key itself. Second one is going to be your self dot vertices of 0, and the third one is going to be self dot vertices of 1. And here, before we iterate, I'm just gonna put this part here as this is going to be vertex, this is going to be the parent, and this is going to be weight at the vertex. So this code is going to run perfectly fine, right? But you need to run this prims here. So you print the graph, print the edges. Lastly, I'm gonna come here and say graph dot print me the vertices. So let's try to run the code. So here is this list, guys, if you can see. So just give me a moment. So for vertex 1 and the vertex 2, so you have added this list with none and max size, none and the max size. So I don't know what we did wrong here. So the parent is supposed to be none and the weight is supposed to be this max size, I think. And the printing, we did something here and there. Let me check. Okay, so self dot vertices of key of 0. So here we are, guys. Vertex, parent, and the weight. I hope this makes a sense to everyone. Can I get a smiley from all of you? So we are exactly at this step, right? So you need to maintain two more lists, visited and unvisited vertices, right? So by default, you can come here and say that in your graph for executing this prims as algorithm, so we want to execute the prims as algorithm. In my graph, I'm gonna have this self dot visited vertices, which is an empty list, and self dot unvisited vertices, right, is a list. So for your vertex addition, I'm gonna say self dot unvisited vertices dot append the edge dot vertex 1, and same way append the vertex 2. So with this printing the vertices, I'm also gonna come here and say print visited vertices, self dot visited vertices, and unvisited vertices, self dot unvisited vertices. So you run the program. Visited vertices is empty and unvisited vertex is 0. So guys, you have the adjacency list if you can see now. So 0 has neighbors as 1 and 2. You have this data coming up for you. So now you need to apply your Prim's algorithmic technique and try to proceed further. We'll be also proceeding it, right? I'll also try to help you guys in implementing this Prims. But I hope this has given you a very good start to implement the algorithm. So this will be all for the day. So in case you have any acknowledgements, I mean you have any queries, you can ask me. I will help accordingly. So Prim's algorithm, partial implementation. Yes, I will be sharing the Word file over the chat, guys, right? All right, guys. So a smiley awaited once again from all of you so that we can close the session. If we are good to go. Great, guys. Thank you so very much. Thank you. Bye-bye, guys.